Hi, welcome to another edition of Linear Algebra. Today we are going to start a new section on applications of linear systems. You'll be happy to know that we are leaving behind that theoretical section on span and linear independence and going to topics that you see in your other engineering classes. Let's go see what we have for today. We have a list of topics here. Have six of them. Perhaps we're going to cover half of these. So item number one, we are going to talk about resource allocation, two, balancing chemical equations, three, network analysis, four, basic electrical networks, five, linear economic models, and six, finite linear games. Sounds like a title to a Jeopardy game, so maybe you go ahead and choose your favorite at 200 to begin with. So let me just briefly say a few words about each of these things, and then we are going to have short videos on a few of them. So resource allocation, what does that mean? Resource allocation, well, we are living in a world where resources are limited, and we have a variety of needs. So we try to do the best we can with the limitations that we have and the constraints that operate on us. This is a very common problem in a variety of areas in mathematics itself and in engineering. Those of you who are considering something in between mathematics and engineering, this topic is ideal because it has a foot on either area. It's typically courses referred to operations research, sometimes offered in industrial engineering departments, cover this topic. It's a very rich area of mathematics. It's a field all by itself. It's also a very lucrative area of mathematics, meaning the pays are very high. Okay, we are going to have a couple of examples, very simple examples of this. Next, balancing chemical equation. This one you remember from high school, perhaps your chemistry classes. Here I've written an example. If you combine CO2 and water, you get, this is C6H12O6, that's glucose. And O2 is, of course, oxygen. What we want to be is to be a perfect chef. We are cooking these things and producing those, and we want not to have any waste left. We don't want to waste anything. So the question comes up, exactly how many of the molecules of CO2, how many molecules of H2O should we combine so that we make the glucose and oxygen and there's nothing left over. Okay, in high school you see this problem, and probably the shortcuts that you have there is going to be shorter than what we are going to do here, but we want to say these are applications of linear systems. Each of them make a very substantial use of linear systems of equations. Okay, next item up, network analysis connects to traffic. Well, that one you know what the traffic looks like, so I don't need to explain that. Basic network, electrical networks. We are going to learn about Kirchhoff laws. Basic here means our electrical networks just have batteries, wires, and resistance. Nothing fancy to it, so essentially like your basic flashlight. But it leads to quite interesting problems in mathematics. Okay, linear economic models. This from the area of economics, sometimes referred to as Leontief input-output analysis. So you might see this in your economics class. And finally, finite linear games. An example of that would be lights out. Well, let me make a guess that of these six topics, your mind goes to the last of these things because of this word here, games. So let me just go ahead and show you what this thing is getting out of the way. Perhaps it's going to entice some of you to go study this thing on your own and see how field of mathematics is rich. The games you might buy at your favorite Xmart has something to do with mathematics. Well, Here's a nice website I found. Let's see, take a look. Well, this what you had seen before. Let me see. Sorry. Okay, this is a page of zillions of puzzles, and this is one of them. This is lights out, probably hard to find in local stores, but you can find used ones and such. Here's let me explain to you what this one is. So let me go turn this thing on, and let me a moment. Okay, so this is an example of a mini lights out game. What how do you play this thing? Well, if you press any button, that button and all the adjacent ones, horizontal and vertical, turn on or off. Okay, so somehow every light is connected to 4 other neighbors, and they all go on or off together. Well, what happens if you do this thing at a corner? The way this is set up is that the left side of this connects to the right side. So when you click on this thing, that corner also turns on, and top of this also connects to the bottom. So you have to kind of imagine that there is a neighbor up there, and that neighbor has been connected to the one down here. So if I go turn it off, you see what happened. Like here, try to imagine who's going to turn on and who's going to turn on, which cells are going to turn on. So when you click on this thing, of course these neighbors are going to turn on, and the left neighbor of this thing connects on the right, and so on. So of course, if I click on the bottom, the problem is easier to look at. These 4 neighbors go on and off. Well, how do you play this game? What are you supposed to do? There are certain number of puzzles here, or you can create a random puzzle here. The question is, somebody has turned on these lights in some style. Can you actually turn all of them off? Can you click on a certain number of buttons here that will turn off all of these lights? So that's why it's called lights out. So interesting little game, and perhaps more interesting is that, well, there's a mathematical explanation for the procedure, and you can read about it, or perhaps you can do it yourself before you go read somebody else's work on it. So a nice little game, and as I said, this page has many of these things. Okay, so I'm going to leave that out, and then you're going to study yourself. And those of you interested in chemical engineering or chemistry or something like that, we're going to take a look at some pictures for that as well. Okay, so we did the exciting stuff, describing what games you're going to play. Now let's go ahead and do some simple mathematics. The first item here, resource allocation. We are going to take a look at a simple example of that. So resource allocation. I'm going to take a look at a few problems, and the best way to describe this thing is just to make a table similar to something you might see in your textbook or in your problems. So in one of these problems, we have a biological laboratory that is growing certain bacteria. Now, I understand this is not a good kind of a problem for these days, but let's suppose that this lab is very careful and they know what they're doing. So we have 3 types of bacteria. So they're called bacteria type 1 or strain 1, and then there is strain 2, and then there is another one, type 3, and they live on certain type of food. So we are going to be kind of a chef that is feeding these uh, bacteria uh, in a petri dish or something with some kind of food, and they have a daily regimens on that they live on, or is best for them or something. So it is measured in some units, however they measure it in a biological lab. This uh, bacteria needs 2 units of type A to eat, needs 1 unit of type B, and 1 unit of type C to eat. Type 2 has more appetite, it needs 2 of this and 2 of this and 3 of this one. And type 3 is even more appetite for food type A, does not like food B at all, and eats a little bit of this food type C. Okay, so we have a description of here. There are certain bacteria, they eat certain type of food, and we are measuring how much of these things they need every day. And so this is presumably like one petri dish, or certain number of units of this bacteria eats this many units of food A. Okay, now then we come and specify some constraints, like perhaps our laboratory gets a certain amount of these type of foods on a daily basis, like the food delivery. So perhaps it's online delivery. Food type A, they get 2,300 units of this delivered to them, and this one they have 800 units delivered to them, and this one they have 1,500 units delivered to them. Well, what is it that we want to do? We want to know that with this kind of appetite and this much food available, how much of each type of bacteria can we grow in our lab. So let's call this thing x1, meaning we are going to grow x1 of these, or x1 petri dish of these, and this one x2 and this one x3. Perhaps you wanted to call them xyz or something, it would be easier to write that way. So the question is to find x1, x2 and x3 so that all this food is consumed and nothing left over, if that is possible. Okay, so this is an example of a resource allocation. We have some constraints, and then you want to know in this problem simply how to plan for how many of these you can grow in your lab. Well, kind of sounds like planning a wedding or something. So you might be having some budget for certain number of food, and you have to know people's appetites, and then you know how many of each type you can invite. I guess that's not very realistic, but it's just something that came to my mind. If you don't want to talk about bacteria, perhaps you talk about something a little bit happier than that. Okay, the question is well, how do we set up the equations? We have certain constraints. The food type A, we have daily delivery of 2,300 units of that. So type 1 bacteria is going to eat 2 units each, and if I have x1 of these petri dishes, they are going to need 2x1 of, so the consumption of type 1 bacteria of food A is going to 2x1. This one also is going to consume, per unit of these things, they are going to consume 2 units of food. So if I have x2 unit of this bacteria, it's going to be 2 x2 unit of the food type A. This one eats a lot more. So if I have x3 units of this thing, and each of the petri dishes needs 4 units, then 4x3, that's what these guys are going to eat. And Well, they are gonna they definitely cannot eat more than 2300 because that's all the food we have. So of course it's a possibility that maybe they eat less, uh, but let's suppose that they are going to clean their plates and eat all of this food. Well, same thing for food type B. So I'll have 1x1 plus 2x2, and this one doesn't eat this at all, and that's supposed to be 800 units of food type B. And last, 1x1 and then 3x2, and then we have 1x3 that is supposed to be 1500 units. Well, our main advertisement is that when you consider this simple application problem, what you are coming down with is a linear system of equations. Okay, where simple application leads to a linear system. Well, then what? Well, we go ahead, solve this thing. We have learned how to solve linear systems. We know from our experience you can end up with three scenarios: no solution, or one unique solution, or infinitely many solutions, and so on. That's for the mathematical side. And then we come to the applications. Application problems have their own additional restrictions and constraints and such. Certain things that make perfect sense in mathematics might not make sense in daily life. So we are going to see certain additional restrictions that are imposed by the application that you have in mind. Okay, so what do we do with this thing? We go ahead, convert it to a matrix. So of course 2, 2, 4, 2300 is my right hand side, and 1, 1, 0, and 800, and then it's a 1, 1, excuse me, 1, 3, 1, 1500. So that, if you remember, that's on my right hand side. And then I go ahead and solve this thing. Okay, this problem is friendly enough for you to attempt to do it by hand, but just to practice that nice little thing we had, let me go bring that up. So we had a nice Gale web page where well, we want to edit this. Let's practice this thing. It's a 3 by 4. Okay, it's a 3 by 4. Okay, it's 3 by 4, and then I have what were my numbers written here? Sorry, 2, and then it was a 2, and then 4, and then 2300, and then 1 and 2 and 0, and big numbers on the right, and then 1, 3, 1, 1500. Okay, we check our numbers, make sure we entered everything correctly, because that's the costly mistake to make here, to restart the whole thing. It looks like I wrote my numbers correctly, if I can see right. Okay, we clicked on that button here, clicked on the resume button here, and then what? Well, we said that we want to, easiest way to think about this thing, you have a number of choices, large number of choices here. So let's follow some strategy. I make this unit, which simply means divide the whole thing by 2. I made that. Okay, I'm going to use this as my pivot, and that as a target. How did we do that? Click on this and click on that, and then again, this is a pivot, that's a target, so you have to click on that again, and this one again. So that we did a Gaussian elimination for the bottom 2 entries here. Okay, this is already 1. I don't need to do anything, but if it was some other number, you click on here and click on R2, and makes makes the pivot to be 1, so it's kind of easier to follow what's going on. Okay, with that pivot, we said we clean below so that we make our echelon form. So here is my echelon form, and then we said we clean the bottom and then we clean the top. That was the efficient way of doing it, but right now the computer is doing everything for us. We don't really feel any pain, or we are not sweating or anything, so efficiency perhaps is not our main concern. So I can use it and erase the number above it. That is so we are making these pivots to be 1 and everybody else is becoming 0. Okay, let's take this thing and turn that into a 1 as well, which means what? This is like 3z equal to 1050. You're simply dividing by 3. How do you divide by 3 here? You just click on that side button, margin button, and it does it for you. Now we use this to eliminate that entry and then add that entry. So this one, we eliminate that entry, and this, we eliminate that entry. Okay, so what does that mean? I guess it would have been easier to call them x, y, z. This really reads 1x equals to 100. These guys got eliminated. This means 1y is equal to 350. This means 1z is equal to 350. So when your coefficient matrix becomes like this, just ones on the diagonal, everybody else is 0, we call that the identity matrix. We are done. We are done. And this, when it's in that form, it really reads x is equal to 100. Or if you wish, x1 is 100, x2 is 350, x3 is 350. So we are done with that. Of course, again, this was a very simple problem, and you could have done it by hand. And so maybe you do it by hand one more time, but since we are pressed for time, and I guess I'll be boring you to tears if I do every one of these things by hand calculation. We ended up with 100, 350, which really means, so this means 1x1 really, so 1x1 is just x1, of course. X1 is 100, x2 is 350, and x3 is 350. Okay, now a general issue in application problems, we always have at least 3 stages. One is to convert our problem from whatever application it is to a mathematical statement. So this, I mean, having a biological lab is one thing, coming up with this table and this equation is something else. So there's always a translation stage or step from your application to mathematics. So that's stage 1. Then stage 2 is that you have in mathematics some equation to solve, you solve it. Okay, so we have done that. Then there is a stage 3, which is, well, understanding what is it that you got. What do these things mean? Well, x1, x2, x3 for us meant how many of this type of bacteria or that one can I grow in this lab given these restrictions and given this appetite level. Well, it turned out that I can have 100 units of this type, well, 100 petri dishes of this, 350 of that, 350 of this one. So one important issue that we have here is that when you have some issue in science, you have a quantification stage, so which converts your problem to a problem in mathematics. Well, in high school you refer to this thing as a word problem. Word problem, everybody hates word problems because, well, you have to grow up. You have to grow up substantially to convert our observation in science to mathematics. So that's a quantification, and then we have the mathematics, We do the mathematics, and then we have an interpretation of what is it that we got. And then we have an observation on this observation, and we go back to our laboratory to see if what we got out here actually makes sense. Okay, so we are presenting to you a pink world where everything just works out, but in real life things you have to go through them several stages and iterations until things actually make sense at all levels. So there are layers and layers of these processes in an actual lab. Here we are just referring to the cleanest version of the whole thing. So we get here, we have our problems already done. Okay, that's how many of these type of bacteria you could grow in your lab. Okay, is that all there is to it? Well, let's take a problem and modify the numbers a little bit. So again, I abbreviate this so we move quickly. Type 1, type 2, type 3, and then food A, food B, food C, and here are slightly different sets of numbers, and the question is well, if I change this matrix of let's call it the appetite matrix. Okay, we have an appetite matrix, and then we have certain levels of food promised to us on a daily basis. Suppose this is what we are going to order. We are looking for the same issue: how much of this and that we can grow. So food type A, 1x1, and of course 1x2 and 1x3 has to, if they eat up the whole thing, that has to add up 1500. And the 1x1 and 2x2 and 3x3, I'm writing the ones so that you see it just coming from there. Otherwise, of course, no mathematician is going to be caught alive with writing 1x1. And then 1x1 plus 3x2 and then 5x3 is equal to our last number, 4,500. Okay, so we have again a linear system, and well, what do? Well, again, you of course just go solve it. So let's go back to this, and we are gonna well, edit, I guess. I go ahead and change my numbers. 1, 1, 1, 1500. Okay, if the size were different, I could change the columns and such, but the size is the same. So this was 1, 2, 3, 3000, then 1, 3, 5, 4500. Okay, I finished my editing. I double check my numbers to make sure I didn't mistype anything. I don't want to do this thing a second time. And then I say resume. Okay, pivot, target, pivot, target, pivot, target. What happened here? The entire row became 0. Well, let's continue the Jordan style. We said, okay, this is called the pivot. I can use this to eliminate item above and below. Okay, I did that. Can I do anything else? No, I cannot. That's the end of this thing. I cannot use this as a pivot, because if I try to eliminate that, what happens is that that entry is going to come non-zero. It is not going to help me. It's just going to be, making an equivalent system. I would not be gaining really much. Okay, this was one of those weird situations that because this thing became 0, situation is different. If the right hand side were non-zero, what would we say there? Let me see if you remember. If this is 0 and the right hand side is non-zero, what would you say? So this was our prompt for getting you to think and remember some stuff we have done before. So the question is, here is the question. Suppose this is still 0 and this is, I don't know, 100, 200 or something. What do you say? Of course you say the system is inconsistent, doesn't have a solution, because it can't be that 0x plus 0y plus 0z is equal to a number other than 0. That would be impossible. Okay, fortunately here we are still possible, but then what? The thing is, our last variable, the amount that we are going to grow of type 3 bacteria, becomes a free variable. Okay, let's continue this thing on paper so that I can write what I'm going to write. So we what we did is, okay, write this thing as a matrix. So we had 1 1 1 1500, 1 2 3 3000, 1 3 5 4500. Do the Gauss-Jordan magic. So Gauss-Jordan magic, and you come out with 1 0 minus 1 0 1 2. This was 0, this was 1500, and the last thing was all zeros. This was the right hand side. Okay, 0 on the left and 0 on the right. Yes, okay, you still have a hope of solution. If this blue thing was non-zero, it would be impossible. Okay, which we said is an entirely different topic altogether. We are not going to look at that now, other than saying it's impossible. Okay, and then what? Let's rewrite this thing in a conventional way. So 1x1 minus 1x3 is equal to 0, and this is 1x2 plus 2x3 is equal to 1500. Last equation just falls out. There's nothing there to write other than 0 is equal to 0. Then what we are going to do is that we are going to take the we are going to call this x3 as the free variable, and we are going to take all of this. We're going to take all of that free stuff to the right hand side, which is going to make it look like x1 is equal to what there was a 0 there, and then becomes plus 1x3, and x2, there was always a 1 in front of it, but let me write it, and that was 1500 minus 2x3. And then what? You said the style is a matter of style. The free variable, we use some other kind of letters to flag for ourselves that has been declared free. Okay, so we call it, say, t, and then everybody gets to be written in terms of t. So this becomes 1500 minus t, and x1, that's just t. So we have x1, x2, x3. So that's how we used to write this stuff. Well, this is t and 1500 minus t, and then a t again. And to separate the numbers and the free parameters from each other, we create different vectors, sort of separating oil and water. So these are all of my numbers, all the t's. I factor a t, and then I get what? 1 minus 1 and a 1. Okay, the beginning of a semester, we saw these kind of things, and we looked at it from the point of view of geometry. Okay, it was no biological lab or anything. It was just, we're talking about points and lines and planes and such. What was that in that context? Do you remember what kind of a creature, what kind of a creature in geometry, what kind of creature in geometry was that thing? That was a starting point, and that was a direction vector. So this whole thing is a line living where? Well, this is a three-dimensional board, and this is going back to chapter section 1. This is a line in R3. That's how we looked at it there. Now what does it mean? Now it means how many units of bacteria you're going to be growing. So all of a sudden, from geometry we're going to biology. Who's T? T is some kind of a free number. Means what? You have a leeway of maybe having more of, you have a choice of which one of these things you want to grow. You can perhaps grow more of these, and perhaps that's going to cause you grow less of that one. It's kind of a trade-off between these. In the previous problem, it was perfectly fixed and done, and there was nothing to go. If you want to consume all that food, then you can grow. You're supposed to grow these many of these bacteria. Here, there you have a trade-off. You can choose to grow. Okay. So what happens if I grow bacteria number 3 a lot more? What happens is that I'm gonna get rid of this population. So it's like playing politics with the bacteria that you have. If you give more food to 1 and 3, you are starving X2s, or you're not growing that type. That's gonna decline. You're forced to have fewer of these. Okay, so that is that's the meaning of a T, or a parameter here. Now, what else? Well, there is additional restriction that comes from application problem that we have in mind. We are growing bacteria. We are not solving a problem in mathematics. We are not really looking at the line in R3. These are living things. So what restrictions do we have to worry about here that were not there when we were solving this problem as a mathematical problem? So again, here is my cue to you that you have to think and tell me, what are the things to watch out for? What do you mean? Well, can I use any T I want? Well, we called it previously a free parameter. Anything you want, anything goes. Well, in real life, anything doesn't go. It's just you have additional restriction. So, for example, can I take T to be 5, 100? That sounds reasonable. If I put 5 here, this becomes 1495. This becomes 5. How about 100? Well, this becomes 1400. 1000. This becomes 500. What if I choose T to be 1500? Well, X2 becomes 0. What if I choose T to be like 2000? This becomes minus 500. What's wrong with that? Well, you cannot have negative number of bacteria. That doesn't make any sense. So mathematically, your variables could be anything they want, but in real life, maybe you have some restrictions. So obviously, T, the maximum it can be is 1500, because if you go over that, this becomes negative, which doesn't make sense. Item number 2. Suppose these were people that you were inviting to a party, and you were feeding them chicken and something, and you want to decide how many guests you can handle every day. Well, of course, you cannot have 2.5 guests or 3 guests or something like that. So first of all, T itself could not have been negative, because none of these things have to be negative. So what we have is that X1 and X2 and X3, all of them have to be at least 0. So maybe I write it 3 times. I was trying to avoid writing too much, but okay. So our X1 is positive, X2 is positive, X3 is positive, or 0. So that's a typical restriction in application, and you have to work in non-negative numbers. Item number 2, if these are like number of people or animals or something like that, that has to be a whole number. So t then will be limited to being a 0 or 1 or 2 or all the way to 1500. So that means 1501 choices you have for uh, uh, sorry, I made a mistake in this quick talking. Let me see my mistake. Maybe you weren't paying attention and I wasn't. This was I from here to here I've forgotten my 2. Oh, sorry. I let's fix this thing. So, well, the discussion that t has to be positive, that's same as before. Now 1500 minus 2t is non-zero, means 1500 is larger than 2t, and then this means t is less than 750, at most 750. So t, okay, so my mistake here, this was supposed to be a 2 here, which changed the problem a bit. So that means what? That means I can, t is 1 of, so if t has to be a whole number, it's either 0 or 1 or 2 or 750. So 1 of 751 numbers, whole numbers, it can be. Okay, so when we were talking about this issue in terms of lines and such, there was no talk of being positive or whole number or something. Any number was fair game. Now it isn't. Okay, next up, let's see what else can we do today, and that was maybe chemical reaction. We throw in the mix too, and then do a separate lecture for the other ones. So CO2 and H2O. I have CO2. Okay, so changing gear to chemical, so we are doing balancing chemical equations. So we said we are making glucose here. That's usually what happens in plants when they create glucose and oxygen. Did I write this thing correctly? C6H12O6. My chemistry is not good. Okay, so this is X, Y, Z, and T. Meaning I don't know how many of these. Okay, two things. How do we, so here we again a 3-stage process. There's some scientific phenomena that's going on. We go and quantify it. All these number indicates that we have done some analytical work. We know that CO2, there's 2 oxygens and 1 carbon atom here, 2 hydrogen, 1 oxygen atom here, 6 carbons, 12 hydrogen, 6 oxygen, and the molecule of oxygen just 2 in it. Now we want to pick out how many of this, how many of that, how many of that, how many of that do we need. Well, before we get into it, what are the restrictions we expect in advance? Of course, X, Y, Z, and T are going to be whole positive numbers for us. Okay, whole positive numbers. Fractional numbers are not, they're kind of frowned upon here, and you could justify by tradition. They have to be whole numbers. So here are restriction X, Y, Z, T, whole positive positive numbers, all positive numbers. Okay, what does it mean balancing? Balancing means left has to balance the right. No matter is being destroyed, nor is it being created out of thin air. So whatever carbon you have here, you have to have the same thing on the other side. So what does these numbers mean, 2 and 2? It means, well, of course, you know, for the water, that's the most famous one. You have oxygen, and then you have hydrogen connected to that. There are two atoms of hydrogen attached to one single oxygen. So this counts as two hydrogens here. If you pick Y of this molecules, a water molecule, then you'll have two Y atoms of hydrogen. So on the other side, it has to show up. So that means for you that 2Y has to be equal to, on this glucose, you have 12 of these guys. So that's going to be 12Z. Maybe I take a short pause here to show you a picture of this glucose. Trying to find a nice website, but I'm not, probably you find a better one than I do. So this is the glucose molecule, the one that we're talking about. These are the oxygens, the red ones. The black one is the carbon, and the white one is the hydrogen, and that's the stuff of life. So we are balancing here. We say on the left you have the water, Y number of molecules of water, so it'll be 2 Y atoms there. So this becomes when you are balancing hydrogen, that's what you get. And then how about balancing the carbon? What do I write here? On the left, how many carbons do I have? Of course, I have just one X. On the right, I have 6Z. So they don't show up anywhere else. Well, only oxygen is showing all over the place. So on the left, I have 2X, and then I have 1Y, and then on the right, I have 6Z, and then I have 2T. Okay, so perfectly sure that you had some shortcuts for solving this thing in high school if you took a course in chemistry, and feel free if you want to apply that. But what we are trying to say here, what we are trying to sell is, look, this is a linear system. Now you kind of messed up, but if you bring everything to one side, so X, let's write X, Y, let's write X, Y, Z, T. First equation reads 1X minus 6Z is equal to 0. Second equation reads 2Y minus 12Z is equal to 0. Third equation reads 2X plus 1Y, and then we bring the other stuff here, minus 6Z minus 2T is equal to 0. Okay, so it's a linear system, and then you go ahead and solve it like any other linear system you have. For sure you are gonna have one parameter, because we can tell whatever number you find here, you can double it, it's still correct, you can triple it, it's still correct, and so on. So it is the convention that the numbers that you get, not only they have to be whole positive numbers, but also they have to be reduced, meaning we don't want to multiply everything by a certain number and create some huge numbers for us, but we want to have smallest whole numbers that work in the equation. Okay, so I'm going to let you go ahead and solve that and find xyz. There's going to be one free parameter, and then you uh, choose that parameter so that all of your answers are going to be whole numbers and reduced so that there is no common factor between them other than 1. So in mathematics we call them relatively prime, but as I said, their least common the greatest common factor has to be 1. Okay, let's move on to more interesting stuff. So this is kind of a very simple application. It's not really showing the glory of linear systems, so that's a little bit too easy. We are going to go to the next two. Three still kind of simple examples we are going to look at, and by the time we come to number 4, even the simple examples become a bit challenging. Okay, so until next lecture, good luck and God bless.